Welcome back to my channel, Study Buddy AIML. I am Vedanshi Khare. Today, we will explore neuromorphic computing, focusing on brain-inspired approaches for engineers. We will cover what it is, how it works, why it matters, and where it can be applied. The goal is to give a practical understanding, not just theoretical idea. The first topic we will be covering is why do we need a new computing model? Modern computing systems consume massive energy, especially while running AI tasks. A significant portion of energy is spent moving data between CPUs and memories, not actual computation. Edge devices like robots, sensors, or drones need intelligence all the time. But we have very limited power budgets. In contrast, the human brain can perform highly complex tasks only about 20 watts, showing what is possible with more efficient computing model. That motivates the development of neuromorphic computing, which mimics brain efficiency. The next topic we will be discussing is how traditional computers work. Traditional computers follow the Van Neumann architecture, where the CPU is separate from memory. All instructions are executed sequentially, and the system is clock-driven, which means it needs continuous consumption of power. Even when the idle or waiting for data, the CPU and memory still uses energy. This architecture works well for arithmetic, logic, and standard computing tasks, but it is inefficient for adaptive, real-time sensory tasks, which can brain handle effortlessly. Now we will be covering how the brain works. The brain consists of millions of neurons, each capable of processing and transmitting information through spikes. Unlike traditional computers, the brain operates massively in parallel, handling thousands of signals simultaneously. Neurons are event-driven, meaning only fire when triggered, which saves tremendous amount of energy. Another key difference is that memory and computations are correlated. Unlike in CPU, memory is separated from processing units. These architectures allow the brain to perform highly complex tasks with only around 20 watts of power. Next, we will cover what is neuromorphic computing. Neuromorphic computing is a completely different approach to computation inspired by a brain. It is not just running neural network on a chip, it is about designing hardware and a system that mimics neural dynamics. Key principles include event-driven processing, where computation only happens when spikes occur, and local learning rules, where connections adapt anonymously without a global loss function. This approach enables massive parallelism and ultra-lower power operation, making it ideal for edge devices and adaptive real-time systems. Now, the topic is mental shift, traditional versus neuromorphic computing. Engineers need a mental shift moving from a traditional computing to neuromorphic computing. Traditional systems are instruction-driven, synchronous, and centralized, whereas neuromorphic systems are dynamic, asynchronous, and distributed. In traditional computers, the CPU constantly pulls memories, wasting energy. In neuromorphic systems, computation happens only when events occur. Spikes carry information, And memory is co-located with computation, enabling high efficiency and low latency. Understanding this shift is critical before designing or programming neuromorphic hardware. Now, our next topic is neuron as an engineering primitive. In neuromorphic computing, the neuron is a fundamental building block, not just a mathematical function. Each neuron integrates input over time and internalized the state can decay if not activated. This is neurons. Each neuron exceeds the threshold, it generates a spike, which travels a connected neuron. This makes neurons stateful, nonlinear, and ideal for temporal pattern processing, unlike stateless arithmetic units in traditional CPUs. Engineers should think of neurons as a tiny, event-driven dynamical systems rather than just a logic gates. Now, we will covering spikes as the data. In neuromorphic system, spikes themselves are data. A spike is a simple binary event, but when it occurs, matter, timing and frequency encode information. This is fundamentally different from traditional neural network that uses continuous value activations because spikes are sparse and only generate when needed. Neuromorphic systems are extremely energy efficient. Think of this as an event-based computation, similar to interrupts rather than continuous polling. Now, our next topic is spiking neural network. Spiking neural networks, or SNN, are primary computational model used in neuromorphic systems. Unlike traditional artificial neural networks, SNN operates in continuous time and communicate using discrete spike events. This makes them specially well suited for temporal data, such as audio signals, sensor streams, and event-based vision, because neurons are mostly inactive and only spikes when needed. SNN can achieve sparse computation and very low energy usage. Conceptually, SNN are much closer to biological neural networks than standard deep learning models. Now, our next topic is learning in neuromorphic system. Learning in neuromorphic system happens locally, meaning each synapse updates itself based on the timing of spikes. The most common rule is spiking time dependent plasticity, or STDP. If one neuron consistently helps another fire, their connection strengthens. If not, it weakens. Unlike deep learning, there is no global error signal, no backpropagation, and no centralized training phase. Learning emerges from local interaction, making neural morphic systems naturally adaptive and well suited for real-time environment. The next topic we will be covering is what is neuromorphic computing. Neuromorphic hardware looks very different from the CPUs and GPUs. Instead of few powerful cores, it uses many small, simple cores, each with its own local memory. This co-location of memory and computation eliminates the cost of data movement seen in traditional architecture. Spikes are communicated through routing network, much like packets in a network on chip. Precision is kept low, or many systems use mixed signal designs to further reduce power consumption. The result is highly parallel and energy efficient architecture optimized for event-driven computation. Next, we will be covering examples of neuromorphic chips. Several research and commercial platforms demonstrate neuromorphic computing in practice. Intel's Loihi focuses on flexibility and on-chip learning. IBM True North emphasizes energy efficiency but uses fixed networks. SpineNaker is designed to stimulate large-scale spiking networks in real time. Brainscale uses analog circuiting to emulate neural dynamics much faster than real time. Each platform explores a different point in neuromorphic design space. Next topic of ours is neuromorphic software stack. Programming neuromorphic system is different from traditional software development. Instead of writing step-by-step algorithm, engineer defines model and constraints, neurons, connections, and learning rules. These models are mapped into hardware resources using specialized toolchain. Popular frameworks like Lava, Nengo, and Brian 2 helps bridge the gap between high-level models and low-level neuromorphic hardware. Overall, neuromorphic programming is more about configuration and system modeling than imperative coding. Now, where neuromorphic computing shines. Neuromorphic computing excels in scenarios where power efficiency, real-time responses, and adaptability are critical. It is especially effective in edge devices that must operate continuously on limited power. However, neuromorphic systems are not designed for large-scale training or heavy numerical computation, where GPUs and traditional architectures perform better. Understanding these strengths and limitations helps engineers to choose right tool for the job. Now, there is a difference between neuromorphic computing and deep learning. Deep learning and neuromorphic computing addresses different problems. Deep learning excels at large-scale training and high-accuracy interface, but consumes significant energy. Neuromorphic computing trades raw computational power and precision for efficiency, adaptability, and real-time processing. These two approaches are complementary, not competitors. In many future systems, they will be likely to be used together. Now, we will be covering the key takeaways of neuromorphic computing. Neuromorphic computing represents a fundamentally different way of thinking about computation. It focuses on event timing, local learning, rather than instructions and global optimization. Its greatest strengths are energy efficiency and real-time adaptability, especially at the edges. Rather than replacing traditional AI, neuromorphic computing will work alongside in its future system. Thank you. If you like the video, please like it and subscribe my channel for further informations on emerging technologies. Thank you very much. Bye bye.